Welcome. What I want to talk about today is counting real roots of sparse polynomial systems. So I will spend some time on motivation and background. I will also give you a rough statement of the main theorem. I'll then start going into more background, a little bit of background on Fewnomials, some earlier bounds, as well as some results from number theory that we're going to need. And finally, I'll give a correct statement or a precise statement of the main results and say a little bit more about future directions. So where are we starting from? We all want to solve equations quickly. And for instance, we'd like to solve something like this system of equations. This system of equations has 5 unknowns, 5 equations, 7 distinct exponent vectors occurring in the equations. This system is artificially constructed, but there are many applications where you see systems this nasty or even nastier. And so to understand things, one route one could take is to look in terms of sparsity and to begin to expand the context. So start from the really easy examples and then go on to the harder and harder examples and see exactly what the limits are. That's the basic idea. So we want to solve systems like this quickly. Of course, how do we do this? That's something that we really have to work on still. And more importantly, why? Well, what's the motivation for doing all this? So first off, I want to say that there's a really beautiful relationship between polynomial equations and complexity theory. And in particular, complexity theory, first of all, is the friend of cryptography. And in cryptography and information security, you want to have ways to hide information or make it difficult for an adversary to steal your information. And complexity theory is all about how hard things are. And also, complexity theory is the barrier to getting better learning theory. So complexity theory helps and hurts, and either way, you have to understand it. It's also something which gets in the way of numerical computation as well. Now, from this point of view, you could just think of polynomials as circuits. So what do I mean by that? I mean circuits in the sense of engineering. And what I mean is simply a polynomial is something which it's a variable, so it spits out values of some kind. And in electrical engineering, you have wiring diagrams, where you actually have physical transistors and gates. And if you have a polynomial where certain values go in and a value goes out, you can imagine it as a circuit. So in this example, we have a polynomial. At the very bottom is the evaluation of the polynomial. It's going to be a sum of products of sparse polynomials. And the way you can imagine this is that this is a circuit. So at the very top, you're feeding in numbers and powers of x, and you're multiplying together the numbers times the powers of x. So that's constant times monomial term. Then you're adding monomial terms. That's sort of the next level down. That's sort of an addition gate. And then when you have a bunch of sparse polynomials at this level, and then in this lower level here, you're putting all these values together and multiplying them together. And then after you have these products of sparse polynomials, you take sums of them. So this is how I'm getting things. So basically, you have gates which add, you have gates which multiply, and so forth. So this is a basic construction from electrical engineering. And it's a nice way to think about polynomials, and it gives us some different way of imagining them. And actually, it corresponds very much to how you imagine a polynomial as an algebraic expression. So an interesting idea, which has grown over the past couple of decades, is that theorems on the existence of roots over some field actually get you close to the P versus NP problem. We could talk more about this, but that's perhaps a subject for another talk, but I just want to point this out. Also, theorems about the deeper structure of polynomials, maybe how the monomial terms appear and so forth, are closer to the issue of derandomization. In other words, the P versus BBP problem. So there's been some beautiful work recently from Pascal Coran, Pranjal Dutta, Nitin Saxena, Thomas Theroff, various authors, relating very simple statements on the structure of polynomials and their roots to really deep questions in complexity. I highly recommend that you look at their work. And then there's also the work of many, many other authors, which I don't have time to name right now. So that's one angle. One reason you want to understand the roots of polynomial equations is because it gets you very much into complexity theory. And perhaps if you answer questions well enough on the side of roots, you can also answer questions in complexity theory and derive new separations maybe. Now, in a different set of applications, there are applications coming from biochemistry. So recent work on chemical reaction networks makes serious use of exact real root counting for sparse systems. So you actually do encounter sparse polynomial systems in different settings where you're looking at the rates of chemical reactions. This is some very beautiful work of Friedrich Bihahn, Alicia Dickenstein, Magali Jaroli, and Xu in recent years. And it turns out that you really do want to know the exact number of real roots. Even that is useful, not to mention finding the roots themselves. Now, from a different angle, Yu Ren and Lian Zhang have been applying tropical Fewnomials, which is sort of another way of looking at sparse polynomial systems, to the complexity of neural networks inside of learning theory. So that's yet another application of polynomial system solving and trying to understand the roots. And related to this also is some recent work of Bihahn, Dickenstein, and Jens Forsgaard, where they actually worked out a very nice multivariate version of Descartes' rule for n plus Fewnomial n by n systems. So what do I mean? Well, Descartes' rule, as you know, is this basic theorem relating sign alternations in the sequence of coefficients for one polynomial, one variable, to the number of positive roots. Well, generalizing this to n equations and n unknowns is very hard and still an open problem. But Bihahn, Dickenstein, and Forsgaard made major progress, and they found such a result for a particular class of systems. In fact, the class of systems that I'm looking at today, n equations, n unknowns, and n plus 2 distinct exponent vectors. Now, the key, though, is that Descartes' rule gives you just an upper bound. It doesn't give you an exact count. And the same is true for the multivariate version. So the question is, what do you do about exact counting of real roots? So before I say more about that, I want to say something about the hardness. So actually, even just detecting real roots, are there any real roots at all? That's already quite hard for one sparse polynomial in many variables. So the result from some years ago is the following, that if you fix any positive epsilon and you look, suppose it's an algorithm that'll take a polynomial f with rational coefficients and variables, and suppose it has at most n plus n to the epsilon terms. So it has just more terms than n. Okay, n plus square root of n plus n to the 1/3, you name it. And suppose you have an algorithm that'll decide that if this polynomial has a real root, and it uses time polynomial in the bit size of f. Okay, I'll explain that in a moment. Then p equals np. Okay, in other words, it is unlikely for such an algorithm to exist. That is the key problem. So deciding just the existence of real roots is actually very hard already for polynomials that are pretty sparse in some sense. Okay, so what do I mean by this size business? First of all, we're using the Turing model. So throughout this talk, I'm going to be talking about bits. So bit sizes of inputs and bit operations. So this is how I measure time. And I'm going to be using a certain notion of size for a polynomial. It's a pretty natural notion of size. So it'll be the total number of bits in the coefficients and the exponents of f. Okay. So in particular, this notion of size for a sparse polynomial is going to be logarithmic in the degree. So this is, when I say polynomial time in this notion of size, it's going to be a pretty strong statement. I'm not cheating. I'm not talking about algorithms that are polynomial in the degree. I want algorithms that are polynomial in the log of the degree. Okay, this actually is natural because the size that I'm talking about is really the total number of bits when you write down the coefficients and the exponents. Okay, I'm not cheating. And also, if the coefficients are rational, well, we look at the numerators and denominators in lowest terms. Okay, or if you like, the height of the corresponding rational number. Okay, so if you instead look at n equations and unknowns with a total of n plus 1 distinct exponent vectors, this is actually not so hard, and it winds up being a cute exercise. Apologies. I mean, if you look for one polynomial in variables n plus 1 terms, if you want to decide the existence of real roots for such a guy, one polynomial, one variable, n plus 1 terms, not hard to figure out. You can get an O of n time algorithm, assuming the exponents are finally independent. And it's really not too hard to work out. You can give it to your students and see if they figure it out. But I was getting ahead of myself. Now I can talk about systems. What do we do about systems? So on this slide, I'm just talking about one polynomial and variables, not too many terms. What about systems? So it turns out the counting roots for n plus 1 nomial n by n systems, the roots n equations and unknowns, n plus 1 exponent vectors is easy, but there's some complications. here's the bonus exercise. Suppose you have coefficientsCij's, and let's control things. So now I'm going to start really getting into the details. I'm going to assume the coefficients are integers between negative h and h. Okay, this is a natural way to measure things, and eventually I'm going to talk about algorithms that are polynomial and log h. Okay, that's my coefficient matrix. Let's look at affinely independent exponent vectors, and they have coordinates between negative d and d. Affinely independent, well, different ways of defining that. It's pretty simple. You could just fix one of the vectors and look at the differences with the other vectors and talk about linear independence. That's one way to say it. Or if you like, you can take the convex hull of these vectors and assume that it has positive volume. That's another way to do it. Or you could also say that they don't lie all in a common affine hyperplane. That's yet another way of defining it. So if you have such a collection of parameters, to count the roots of this system, so there you see it's n equations and unknowns, n plus one distinct exponent vectors. Try counting the roots in the positive quadrant, or let's say the real algebraic torus, or in Rn. Turns out you can do it in time polynomial in n plus log dh. Okay, so polynomial time in a rather strong sense. Okay, so this is basically polynomial in input size. You can do it, and this is a nice exercise to work out. So for this exercise, it's helpful to use Smith factorization. This is relatively classical factorization for integer matrices. And also, it turns out you need linear programming, or at least an algorithm for linear programming that works in polynomial time. And this is especially important for the case of infinitely many roots. Okay, so for those experts in the audience, you might say, oh, this is a trivial problem. Yeah, it's pretty easy. But the case where you have infinitely many roots is a little bit tricky. So you actually need linear programming to completely solve this. Okay, that's kind of an interesting way to introduce linear programming to your students. All right, so that is a setting where we can completely solve the problem. But the next step up is what we're going to talk about for the rest of the talk. So n plus 2 nomial, n by n equations and unknowns, n plus 2 distinct exponent vectors. So it is the last tractable case for now, current technology. So the main theorem roughly is the following. If you fix n, fixed number of equations and variables, then you can count exactly the number of roots in the positive quadrant of the real algebraic torus, or Rn, of any generic n plus 2 nomial n by n system, as I've defined it before. Generic, what does that mean? Well, two things. I need the exponent vectors to be affinely independent. That's a mild assumption, just to prevent stupid changes of variables to get you to lower a smaller number of variables. That's a very reasonable assumption. Also, I do have to make some assumptions about the coefficients. So it turns out the case of infinitely many roots for this setting is rather subtle, and I don't know how to handle it yet. And it seems to be somewhat of an open question, despite earlier work. So we're going to make some genericity assumptions to make sure the real zero set has zero dimension. That's going to be one of the assumptions, more or less. And we can be more precise about this later. So the system's over Q, so you can assume the coefficients are rational, or integers. I mean, you can sort of clear denominators if you need to. And you can do this. You can count all these roots in these appropriate places in polynomial time, deterministic polynomial time. So as an example, in under 1 second, we can look at a 7 nomial 5 by 5 system defined by this. Okay, so here you see 5 equations, 5 unknowns, a total of 7 distinct exponent vectors. If you look closely, you see in the 6th term that there's a parameter c. So I'm going to vary this parameter c and just do a bunch of counts. And you'll see the number of roots of the system, or this family, is going to be 2, or 6, or 6, or 2, or 2, or 0, number of positive roots, respectively for these different values of c. Okay, so I picked these values of c because they basically cover all the possibilities for the number of positive roots for this family of systems. Okay, so you can do that all in less than 1 second by the techniques that I'm going to be mentioning today. And the interesting thing to observe is that if you try to put the system into Bertini, Bertini dies. Okay, this is not a criticism of Bertini. I'm just stating a fact. There are many other computer algebra systems that would also die. But it's interesting to see why Bertini dies and how it does so. So Bertini immediately dies and it gives you an error. It says that, I forget the exact statement of the error, but it's something involving numerical error. And Bertini is right, because if you try to plug in a floating point number, if you look at these exponents, they're very large. So most floating point numbers, if you stick them in here and try to evaluate, you'll just get crazy large values. And so yes, Bertini is right. Numerically, this is a really bad system. Nevertheless, you can solve it accurately by the techniques that I'm going to mention today. In fairness, I should also mention Maple, Singular, most other systems will just die. I don't know of any system that actually handles this correctly. There are some codes that will at least tell you the number of roots. So it turns out the number of complex roots. Number of complex roots turns out to be 245 million, or over 245 million. So Johannes Maurice's mixed volume code will tell you this. Jan Verschelde's polyhedral homotopy code will tell you this. But nobody's code, as far as I know, will tell you the number of real roots for such a system, or for this family. Okay. So the key here is that most computer algebra systems have complexity for polynomial system solving, depending mainly on the number of complex roots. But the techniques that I'm using have complexity depending mainly on the number of real roots, and that's a key thing. Okay, so let's review a little bit of Fewnomial theory. So there is this very important result by Buchanan and Satil, which tells you that if you have real coefficients, and if you look at, say, an arbitrary number of exponent vectors, not lying in the same affine hyperplane, and you write a monomial term in this particular way, then there's something called the famous real Fewnomial theorem. And the real Fewnomial theorem is actually due originally to Khovansky, made a major advance back in late 70s, mid 80s. And I put the plus here to indicate the improvement. So Buchanan and Satil made this beautiful improvement. They gave a nice explicit bound, which improved Khovansky's by quite a bit. And you see here the precise bound is here. There have been some improvements here and there, but basically the bound is exponential in k, and polynomial in n if you fix the k. Okay, so you have n equations and unknowns. Where's the exponentiality coming from for the number of non-degenerate positive roots? It's coming from how many more exponent vectors you have than n. Okay, that's where the exponentiality is coming from. So this is an important bound, but the sad thing is that we don't know if this is the correct order of bound, or if this is really how big the number of roots gets. What we do know, there's a paper I wrote with them some years ago, that there do exist systems with this many roots. So basically systems having the exponent should be something like the min of n and k minus 1. The inside is a little bit more complicated. So there are systems with this many positive roots. This is considerably smaller than the stated bound of the real Fewnomial theorem. And there's a big gap, and that's where the devil lies. And however, in certain cases, we do know an exact bound. So actually, back in 2006, Bertrand, Buchanan, and Satil found a type bound for the case k equals 2. The case we're looking at today. So it's n equations, n unknowns, n plus 2 distinct exponent vectors, affinely independent. The correct type bound is n plus 1 for the number of positive roots. Okay, so at least that's known. There's a type bound, but when somebody hands you a system, what is the exact number? It's going to be somewhere between 0 and n plus 1. That's all you know. Okay, now, a very important observation, a beautiful result from quite recently, a result of Peter Bergieser, Alfred Erger, and Josué Tonelli-Cueto, is if you look at random systems, random sparse systems, then it turns out the average number of roots in the real algebraic torus is bounded above by a much better quantity. So I don't want to digress too much here, but this quantity here is significantly better, much smaller order than the bound from the real Fewnomial theorem. Okay, so it shows you that on average, you can expect things to be much, much nicer. Very beautiful result. Okay, so let's get to the techniques that we want to be using. So I'm sorry I'm going a little slow, but I want to make sure we review the different material, and I'll try to finish on time. So there's a lemma you can go back to. Yes, certainly derive this, but it's probably been known earlier. If you want to take a dth root of a real number, a positive real number, you basically need about log d many steps of bisection in order to get a approximate root in the sense of Smale. In other words, a place where you can start Newton iteration to get fast accuracy. So what's the idea? Well, the idea is that if you want to solve something this simple, if you just want to compute a dth root of a number, in other words, solve a binomial equation, you can use bisection. So you look at the graph of x to the d minus c, and you look at the endpoints, and you see on which half of your interval you're going to have your root. And this basically boils down to computing signs. So, okay, you compare two d powers, and you see which one is bigger, and then this is how you carry on your bisection. This is how you isolate roots. You half the size of the isolating interval. This is a basic technique which is ancient. Now, is there a problem with this? Well, there actually is a problem, because if you want to count bit complexity in the right way, it's not easy to compare powers of large rational numbers. So what you do instead is you compare logarithms, and then you bound carefully how much accuracy you need, and you iterate carefully to get good accuracy of an approximate logarithm. That's what you really do in practice. So there's a deep theorem of Baker. It's a bit of an overkill, but there's a theorem of Baker which tells you exactly how much accuracy you need, or at least gives you an upper bound. And so Baker's theorem is a tremendous theorem which tells you that if you have an arbitrary linear combination of logarithms weighted by integers, logarithms of integers, then if this linear combination of logarithms is not zero, then it is separated from zero by a minimal lower bound. Okay, so that's what the theorem is saying. So I have the theorem stated here. It's a little bit hard to parse, but basically Baker's theorem is telling you that for a linear combination of logarithms of integers, if you know the sizes of the integers, then you can bound explicitly how far away from zero you are if you're non-zero. That is a very, very key result and a very deep result. And we're going to make use of something even more powerful in our setting. All right, so what about real univariate trinomials? So I spoke about radicals, I spoke about binomials. So it turns out that even deciding the sign of a trinomial in one variable at a rational point in time polynomial and the size of the polynomial and the height of the rational number is an open problem. There's been some really interesting work done recently by Jindal, who are in that picture here, but it's still an open problem. So bisection here is abstracted. So you can't use bisection so trivially when you're looking at trinomials. So despite nice progress by Jindal and by Michael Sagerloff on coarsely approximating the roots of sparse polynomials, counting real roots of sparse polynomials in one variable, just one variable, is still an open problem. It's unknown how to do it quickly. Okay, we're talking about systems. Okay, so now correct statement of the main theorem. Take any n plus 2 nomial, n plus 2 n by n system over the rationals. Exponents don't lie in a common half in the hyperplane. Coefficient matrix has rank n. And there's a couple more assumptions. You have to assume a couple of 2 by 2 subdeterminants of the coefficient matrix that are non-zero. You can count exactly the number of roots in the positive orthant, the real algebraic torus, or Rn. And deterministic time, this much. So you see here, the bound is a bit killer. It's exponential in n, but I at least managed to work out some key constants and the dependencies. And I'm not claiming the algorithm is practical. What I am claiming is that we finally have a better understanding of the complexity. Okay, so we at least have polynomial time for any fixed n. The practical will of course come later, and I very much would like to work more on this, and as more people work on this. Okay, so the key new ingredients for this result are a refined version of Liouville's theorem. Well, it's not a key new ingredient, it's one of the ingredients. But the real ingredient here is the theorem of Baker and Woods-Holtz. So this is a Baker's theorem on steroids. You basically look at linear combinations of logarithms and real algebraic numbers. And also, it's nice to observe that if you happen to have a really, really strong version of the ABC conjecture, you can reduce the complexity to polynomial in n in the main bound. So that's actually a really, really nice thing to do, but unfortunately it seems very, very hard and really out of the reach of current technology. I could talk about that offline. Okay, so the key idea behind the proof, you use Gaussian elimination on the monomials. So to get the system into a much nicer form, basically you have monomial equal to sum of two monomials repeatedly. And then you make use of a circuit relation. What do I mean by that? Well, when you have a set of points, which is the set of vertices of a simplex plus an extra point, that's called a circuit. And then if you look at the affine relations, linear combinations get you zero. That's called a circuit relation. So for our example, the circuit relation is this. You have 7 exponent vectors and you have coefficients and you sum up to 0. And then if you do a little bit of work, you'll notice that if you have a root for your system, then a certain monomial in the root must be a root of some kind of structured rational function. Okay, so we go from 5 equations, 5 unknowns to 1 rational function. in a very explicit way. And this can be done in general when you have a circuit system of the shape that I'm talking about. But if you're looking at the roots of this guy, well, you can move that 1 to the other side of the equal 0, and you get a linear combination of logarithms. Just take logs. So that is what we look at. So we reduce the entire problem just looking at this. And now there's some additional technicalities involving sign conditions. I should mention the exponents are usually a lot larger, or the coefficients here, but this is just a nice little rigged example. Okay, so what's the next thing you do? You look at the graph of this linear combination of logarithms, and you look at its roots and the number of roots that it has over certain intervals, ones of being the root count for the system that you're looking for. And what you're going to do is a very conceptually simple thing. You use Rolle's theorem. So basically you look for peaks and you see where you cross the x-axis, and it's really nothing more than that. The devil's in the details, though. You need to know how much accuracy you need, and you have to make an estimate for these peaks in a very precise way, so you know exactly what is positive, what is negative, and how close these things are spaced apart. So you basically apply a bunch of major theorems, and the details are all in the paper. And I'm very grateful that so many researchers have come up with so many beautiful results. And that's basically the entire idea. Now, the last thing I want to say, I'm sorry I'm a little bit over time, is that all this work is basically telling us to randomize. So here's an observation. Even though there are n+1 nomial systems and equations and unknowns, and univariate tetranomials with exponentially close real roots, you can build systems that have really close roots. These appear to be rare in practice. And so there's an older result of Mignot on univariate polynomials, and there's a recent result I have with one of my grad students, or former grad students, Yu Zhu, where we actually look very closely at some of these extremal examples and get some interesting results here. So the point is, these pathological examples with close roots are rare. So that's one reason you want to start randomizing if you're going to look at solving. And also, while we can now count real roots in this rough bound, there is growing evidence that we can attain much better complexity. Okay, so in other words, complexity polynomial in n. So if you randomize. So if you go on average, then there is definitely some hope. And this is really recent work of one of my students, Weishun Deng, and Alper Negro, who's now a faculty member at San Antonio, and my colleague Gregorius Powers. And we're slowly working this out. So there's nothing decisive yet, but we're going in this direction, and things look promising. So I thank you for listening to my talk, and I'm sorry to go over time, but thanks again. And I wish you a wonderful stay wherever you are.